Hi there everyone, welcome to the video for lesson 3.1, solving systems of equations by graphing. Today we're going to learn how you can solve a system of equations through the graphing method, and graphing linear equations is something that we have already worked through in our previous chapter. So for our first example, we have the system of equations 2x plus y equals 5 and x minus y equals 1. And what we're looking to do is to graph both of these equations to see where the lines are going to intersect. Wherever the two lines intersect is the solution that both equations share, and since both equations will end up sharing the same solution where they intersect, that means x and y will be the same value for both equations. So as we do with all of our equations when we're about to graph, we need to first put both equations into slope-intercept form. So in the first equation, the top equation, I'm going to be subtracting 2x to the other side. So I have the equation y equals negative 2x plus 5 in slope-intercept form. For my bottom equation, I'm going to also put this in slope-intercept form. First by subtracting x to both sides. And next, I'm going to get rid of the negative sign in front of the y. Remember, this is like having a negative 1 in front of our y variable. So if I divide everything in my equation by negative 1, all of my signs will change. That's a minus 1. So now we have y equals x minus 1 and y equals negative 2x plus 5. And these are the two lines I'm going to graph. So starting with my top equation, my slope-intercept is 5. My y-intercept is 5. So I'll put a point where y equals 5. And my slope is down 2 and to the right 1. And then I can connect my points together for my line. My second equation, y equals x minus 1, I'm going to start at my y-intercept, which is negative 1. And for my slope, I'll be moving up 1 and over 1. And as you're putting your points on your graph, you should see that both of these lines share a common point. The point at which they intersect is going to be the ordered pair 2, 1, which is right here on my, graph. So if you, I'm just going to scroll down a little bit. Intersecting lines, any lines that intersect will always have exactly one solution, which is going to be their point of intersection, which is an xy ordered pair. On this graph, my solution is the ordered pair 2, 1. So I'm going to write that next to my graph so that I know what my solution is. This type of system is an independent solution. And it is also considered a consistent system because it has a solution. The next example we're going to look at, we've got the system of equations 3x plus 4y equals 12 and 6x plus 8y equals negative 16. We have the same goal with this system as we did with the last. We're going to graph both of these equations by first placing them in slope-intercept form, and next we're going to look to see if they have a solution or a point of intersection. So on my top equation, I'm trying to isolate the y variable. So the first thing I'm going to do is subtract 3x to the other side of my equation. And next I want to divide everything by 4 in order to get the y by itself, which gives me negative 3 over 4x plus 3. Now for my bottom equation, I also want to isolate the y variable. So the first thing I'll be doing is subtracting 6x to the other side of my equation. And next I will divide everything by 8 so that I now have the equation negative 6 over 8x minus 2. Don't forget to simplify or reduce your fraction. So if I reduce negative 6 over 8, I get negative 3 over 4x minus 2. And now I'm going to graph both of my equations since they're in slope-intercept form. So starting with the first equation, negative 3 over 4x plus 3, I'm going to start with my y-intercept at positive 3. And for my slope, I'm going to be moving down 3 and over 4. I can also go in the opposite direction and move up 3 and to the left 4. So there's my first line. For my second equation, I've got negative 3 over 4x minus 2. So I'm going to start at my y-intercept, which is negative 2. And I'm going to do the same thing for my slope, down 3 and to the right 4. And I'm also going to go up 3 and to the left 4, since I'm running out of room at the bottom of my graph. And connect my points together for a straight line. So what you should notice about this graph, my second line that I drew isn't perfectly straight, but these two lines are parallel lines. Parallel lines we know will never ever intersect. And since these two lines are never going to intersect, parallel lines have no solution because there is no point at which they intersect, so they don't share any common xy ordered pairs. You can also use the no solution symbol if you don't want to write out no solution. Something that you may have noticed before we began graphing these two lines is that both equations, once we reduced negative 6 over 8x, both equations end up having the same slope of negative 3 over 4x. Parallel lines, as you may remember, always have the same slope, so this is a good indicator before you begin graphing that you should know that you should get parallel lines when you have the same slope for your equation. At this point, I'm going to have you pause your video and begin working on the last example on your page. You've got the system of equations 9x minus 6y equals 24 and 6x minus 4y equals 16. So you can pause now, and when you play the video again, you can check your work compared to my work on the video. Okay, welcome back. You should have graphed the last system of equations. And what should have happened when you did that is once you solved both equations that were given in this system, you should have ended up with the exact same equation, which is 3 over 2x minus 4. I've only shown my work for the bottom equation. So that's what you see the work for here on the screen. So what happens is when you have a system of equations that end up being exactly the same one in slope-intercept form, obviously you only need to graph the line one time because it's the exact same equation. What's really happening is both of the lines that you have, because they're the same, think of them as overlapping one another. Okay? So what happens here is absolutely any point that falls on our line is a system to both equations. So any point that is on this line will satisfy both equations for x and for y. These are called coinciding lines since they overlap each other, since they coincide. Coinciding lines have infinitely many solutions. You may also choose to abbreviate this with the infinity symbol, okay? For as long as this line stretches on, which is forever, to infinity, any point that falls on that line is a solution, making our answer to the system infinity. This type of solution we call dependent. and it is also considered to be consistent. Consistent, again, because it does have a solution. In this case, there are infinitely many, as opposed to the first type of system that we looked at. It was consistent because it had only one solution, but it did have a solution. Our middle example with the parallel lines, because they have no solution, this is called an inconsistent system. All right, thanks for watching. See you next time.